Hey, we're happy to have Ofri Telem visiting all the way from Hebrew University in Jerusalem. Uh, Unfortunately, due to flight problems, he's not here in person. He's going to tell us about quantum spectral method.
Thanks. Flight problems is the nicest way of putting it. Why my flight from Israel got canceled right now. But yeah, I wish I could have been there with you, but Zoom will have to do. So thank you so much for inviting me. And I want to tell you about a research direction that I've been kind of engaged in for the past maybe 3 years or so. And it's kind of an original research direction which aims to solve classical problems by starting from quantum calculations that we know how to do. Now, this is something that has been quite popular in the context of scattering amplitudes, helping us do calculations for black hole inspirals. And this is a little bit of a different take. Here, instead of starting from scattering amplitudes, we start with something that's more similar to what we know from undergrad quantum mechanics, solving something like the hydrogen atom or its generalization for GR. And then from that, inferring things that are very hard to compute classically. So in a sense, naively, you'd think that quantum mechanics just makes things more complicated, but we'll show that in certain contexts, which we will see here, there are classical computations that we just don't know how to do analytically, and we can do them if we go quantum for a second and then take h bar to 0. Okay, so I'll start with a motivation. This is a simulation of an extreme mass ratio black hole in spiral. So this is a small black hole just going for like 1,000 times around the supermassive black hole before plunging in. And the overarching goal of my research program for the past few years was to see if we can compute the gravitational radiation reaction force on the black hole going in an extreme mass ratio in spiral, meaning on the little black hole diving into the supermassive black hole, analytically to some desired order in G Newton, the coupling, and eventually to second order in the mass ratio as well. And if we can use it then to generate predictions for the LISA future space-based gravitational wave detector. Now, for people outside of this field, this might seem like it's some task. It's unclear whether it's very hard or very easy. So to give you just the context, this is a very hard to impossible problem that we're trying to tackle here. Okay, so each order in G gives us another loop order if we were trying to compute it with Feynman diagrams. Okay, and there are current modern tour de force calculations at order G to the 4 or 5. And these take a huge amount of effort. So this is equivalent to very hard things that people compute in perturbative QCD, for example. Okay. Now, the kind of ambitious goal is to be able to do this with a new method called the Quantum Spectral Method, which just brings a completely different take on the problem. And I hope I'll be able to convince you that there's a chance here to make progress in a new direction where progress seemed almost impossible. Okay, and it's not that we know how to compute better than other people. It's just based on the fact that the hydrogen atom, in some sense, is a resummation of an infinite amount of Feynman diagrams. So if we start from the hydrogen atom instead of starting from scattering amplitudes, we might be able to just have much more data in when we do our quantum to classical extrapolation. So let's start with an example how radiation reaction works in a simple system. This is just Keplerian motion. So think of Earth around the sun or a classical electron around a classical proton. So if you ignore the radiation reaction for a second, you have Keplerian motion in an ellipse. And famously, the trajectory is parametrized in this ellipse form, where P and E are constants of motion. They're functions of E and L, the angular momentum and the energy. And now what happens if we have radiation? And of course, things radiate. A classical electron would radiate an electromagnetic radiation as it accelerates. And what happens is you're going to radiate and you're going to lose energy and angular momentum, and you're going to inspiral into the classical proton. And now we can parameterize the true orbit using a quasi-Keplerian parametrization, which is basically taking the Keplerian parametrization and taking these quote-unquote constants of motion to have a slow time dependence, representing the fact that some energy and angular momentum are lost to the outgoing radiation. And now P of t and E of t change slowly with time. And to know how they change, we need to solve basically Newton's second law with the radiation reaction force. And the question is, how do we calculate the radiation reaction force? It should be the Lorentz force from the emitted radiation. Now, in the limit where the time for a single Keplerian period is much shorter than the characteristic time of loss to the radiation, what we're doing is we're slowly moving between neighboring Keplerian orbits. And we can use some perturbative scheme called the post-adiabatic perturbation theory. So within post-adiabatic perturbation theory, what we can do is we can calculate the orbit averaged radiation reaction force, not on the true orbit, but to the desired order in the perturbation theory on the Keplerian orbit, which is momentarily tangent to where we are at the time t. And if we want the next order, well, what we should do is we should take partials with respect to the orbital parameters P and E and multiply them by the dots of P and E from the previous iteration of the perturbation theory. Okay, so from a given order in perturbation theory, we can always go to the next order by computing partials of the radiation reaction force with respect to the orbital parameters. Any questions so far? All right. So the moral of this story is that to set up post-adiabatic inspiral calculation, it's enough to know to order epsilon, the ratio between the periods, the orbit average radiation reaction force on a Keplerian orbit. Okay, it's a functional of P and E, and we can apply it to the changing P and E as a function of time. And of course, that's not the exact orbit. That's just the first order in the mass ratio orbit. And to the next order, we need the partials. So in relevant examples, even though we kind of simplified the fact that we only need to calculate the radiation reaction force on a Keplerian and a tangent Keplerian orbit, it's still not simple enough because this is either known numerically or perturbatively in G at great effort. Okay, each new order in G is like a huge loop calculation. So the question is, can we compute it analytically to all order in the coupling? And can we even try to generalize to GR? And here comes a method that I developed with my very excellent student, Majid Kharaf. I hope that one day maybe he will give a talk of his own at Davis to tell you about the progress on these things. And this method is called the Quantum Spectral Method, and I'll explain. So this is a framework to analytically compute all time-dependent observables, not just radiation, anything, for any conservative motion in a spherically symmetric potential. Okay, so note that even though we have an inspiral, because we're calculating the radiation reaction with respect to a given conservative orbit, the tangent Keplerian orbit, we can use this method, which was made for conservative motion. And it allows us to compute conservative trajectories, the emitted radiation from the conservative trajectories, and also the radiation reaction force. So in this talk, I'm going to talk about the framework. I'm going to prove it to you. It's a simple matter of the WKB approximation, which becomes exact in the classical limit. And then I'm going to show you some applications. So we'll see a non-relativistic electromagnetic inspiral. What's going to be out very soon, maybe next month, is the generalization of this to special relativistic motion and also unbound trajectories. And the fact that you can write one universal expression, which you can analytically continue in a natural way from unbound to bound. And in the works is, of course, generalizing this to gravitational and scalar radiation reaction in Schwarzschild, and eventually to Kerr, because even though everything I'm going to say today applies to spherically symmetric potentials, it's just to simplify the presentation. There's nothing in the quantum to classical extrapolation which needs spherical symmetry. It's just for the sake of the talk. We want to start with something simpler and then look at more complicated frameworks. So here's my talk plan. I'll give you a quick refresher on classical motion and a spherically symmetric potential. I'll present a first glance of quantum to classical relations. I'll show you the master equation of the quantum spectral method and its proof via WKB. And then I'll show you some applications. And eventually I'll summarize. Any questions so far?
So is it easier to do one smaller mass black hole and one very massive black hole compared to like two equal mass?
Yeah, so the idea is there's no free lunches. Okay, so doing a computation like this, which is inherently non-perturbative, requires, morally speaking, the summation of an infinite amount of diagrams. So then you need to be in a specific regime to be even conceptually able to resum these diagrams. So for example, if you're talking about just scattering, you'd want to work in the Icono limit, where you can resum an entire ladder of photons. This is where there's actual resummation. So what I will show is not just for unbound, but also for bound trajectories. If you're close to like a hydrogen atom wave function, then that's like a good resummation of the diagrams. So we're not going to do diagrams, but that's morally the reason why this only has a chance to work where there's some small parameter like the mass ratio. Okay, so a classical refresher. Let's look at the Hamiltonian for motion in some unknown spherically symmetric potential. And the motion is planar just because of spherical symmetry. So let's set theta equals pi over 2 and forget about theta from now on, and also set the angular momentum to be in the z direction. Now, the azimuthal motion is given by phi dot is L over mu r squared. That's just the definition of angular momentum. And generically, what you're going to get, if the energy is negative, the kinetic energy is negative, you're going to get bound orbits, but they're not necessarily going to be ellipses, right? They're only ellipses for a very limited amount of potentials. In general, they'll be precessing and making these flowers. Now, the radial motion is governed by this equation, which you can prove directly from the Hamiltonian. And u of r, the square root of u of r, integrates to what we call the radial Hamilton-Jacobi action, which is another formulation of the classical dynamics. Now, for negative kinetic energy here, we get bound motion between an r min and an r max. And I just plotted this u of r here. And you see that the allowed region where the motion, the classical motion takes place is between r min and r max. Now, the idea, the important thing to remember here is when we think of Keplerian motion, we think of an ellipse. So this has only one period. This is the time period to do one round trip. But generically, a motion will have two different periods, which will not be the same. There's the radial period and the azimuthal period. And we can also define the fundamental frequencies, which are 2 pi over these periods. And it's very convenient to go to action angle variables. I'm not going to give a whole refresher on classical physics here, but the way you do usually celestial motion is you go to these conjugate variables, angles and their corresponding action variables. And the idea is that these angle variables just grow linearly with time, and the rate is given by the fundamental frequencies. The implication is that whatever observable I want to compute, be it the radius, the emitted field, or whatever, is going to be a double Fourier series in these two angles. So this is generically how you would write it. Just the Fourier coefficient times the exponential of the harmonics of alpha r and alpha phi, the two fundamental angles, with the coefficients given by the inverse Fourier, double Fourier transform. And generically, when something is doubly periodic, it doesn't mean that it's periodic, okay? So for example, phi of t in a potential which is not just a Coulomb potential has two periods. So what happens is that it changes shape, okay, over each period. That means that the phi precesses. Okay, so after this quick refresher, let me go very quickly to results, not to bore you with classical physics that you might know from undergrad. So let's take the same Hamiltonian that we used to compute the classical motion and now treat it as quantum with the eigenbasis labeled by the quantum numbers Jr, L, and M. Now, usually we talk about n, L, and M, where n is the principal quantum number, but this is a good parameterization only for the hydrogen atom because the hydrogen atom has a degeneracy, okay, because it has only one period. But generically, the quantum numbers will be Jr, the radial quantum number, and then L and M are the angular quantum numbers. So they're the eigenstates of these operators. Now, morally speaking, we're going to talk about the classical limit. So what happens in the classical limit? Quantum numbers go to infinity. H bar goes to 0. Okay? But their product is something with units of angular momentum, which remains finite in the classical limit. And these are actually the classical action variables of the system. So the Jr quantum number goes to the Jr quantity, which is a classical characteristic. It's a function of energy and angular momentum. Same for the L and also for the M, although because of symmetry, we choose M to just go to the angular momentum of the problem. Okay, so the first non-trivial result, which I haven't seen before, but it's so simple, it has to be buried somewhere in the literature from the last 100 years, but I couldn't find it. Okay, on the left-hand side, we have a classical quantity. These are the classical fundamental frequencies of the system. On the right-hand side, however, we have the differences of the eigenenergies, the quantum energies. And I found it shocking that I did not learn this in undergrad, that these things were actually related. Okay, so if you take the classical limit of the difference between energies, energy levels, in the hydrogen atom, but also in any other system, in a Schwarzschild potential well or whatever, you get the classical fundamental frequencies of the system. And of course, what you have to do is you have to tell the classical system what its conserved quantities are, right? So how do you infuse that information on the right-hand side? What you say is before you take the H bar goes to 0 limit, you set the quantum number to the classical quantity over H bar. And only then do you take the H bar goes to 0 limit. And then you'll get something that's equal to the left-hand side, which is a fundamental frequency, which is a function of the conserved quantities of the classical system. Any questions about this relation? I'm going to prove it to you on the next slide.
What's delta Jr and delta L?
So take any two levels spaced by some delta and just look at this this ratio. So you can choose delta Jr to be 1. It doesn't matter for this identity. It's true for any.
The energies are for the same Jr. Is that right?
No. So the energies. Okay. So the point is that we're used to energy being only a function of n, the principal quantum number, but that's just a specific thing for the hydrogen atom. So generically, for a system with, yeah.
I'm reading it wrong. I see what it means. It's a subscript. I wasn't reading it as a subscript for some reason.
I see. Okay,
Great.
good. So this is true for Coulomb Schwarzschild.
This is independent of this delta J and delta L.
It is independent, yeah.
Looking at the very, big quantum number, something may become independent, or it's just always. It's probably only true for large quantum number.
Well, the quantum number is infinity because before I'm taking the h bar goes to zero limit, I'm setting JR small j to be capital JR, which is finite, over h bar, which goes to zero. So this is strictly in the quantum numbers go to infinity limit. But delta does not go to infinity. The absolute quantum numbers go to infinity, but their differences don't. Okay, so let me just prove it to you. Okay, so the proof is WKB. I start with the Schrodinger equation. And I know that there are WKB solutions, which basically go like the sine of the classical radial action over h bar. So that's already a quantum classical connection, which is known for 100 years, okay, from WKB. And the point is that there's a WKB quantization condition, which tells me that the phase accumulated between the two classical turning points is equal to pi h bar times JR. JR is the number of nodes of the wave function plus a half. And all I need to do is differentiate this quantization condition and I'll get these identities. Okay, so now I take JR at E equals EJRL, and I subtract from that JR at E of JR minus delta JR, and this is just equal to 1. And now I rearrange it as just a partial with respect to energy times the h bar goes to zero limit of the difference between energies. But this quantity is just 1 over the radial frequency. That's a classical formula. So I get the proof of my identity. It's a very simple thing. But just for general amusement, let's see what happens in the hydrogen atom. So you take two energies of the hydrogen atom, you take their difference, and you take this limit. And lo and behold, you get the Keplerian fundamental frequency. So whenever I teach, I'm going to teach quantum mechanics from now on, I'm going to show this to the students. I think it's understandable enough. Questions? All right, so this was just a taste. Now let's go to the bigger guns. So I'm going to show you what the master equation of the quantum spectral method is. So remember that any observable of the system is just given as a W Fourier series, and we don't know what these Fourier coefficients are, right? We have to do a very hard classical computation and maybe evaluate some numerical integrals to know what these coefficients are. The QSM provides a way to pick up these Fourier coefficients as the classical limit of quantum matrix elements. And without further ado, here's the master formula. So on the left-hand side, again, we have a classical quantity. It's the delta JR, delta L Fourier coefficient, classical Fourier coefficients. We put some superscripts JR and L just to indicate that it's a function also of the classical conserved quantities of the system. And that is given as the h bar goes to zero limit of a quantum matrix element with, in the middle, I'm putting the operator version of that operator. This operator could be the emitted field, the radius, the phase, whatever you want, okay? So I'm taking it as a quantum operator. And essentially what I'm doing is I'm saying the quantum numbers on both sides, on the bra and the ket, they're all going to go to infinity, okay? According to this relation, they're going to be the classical conserved quantity over h bar. But the difference between the bra and the ket on the two sides, that's going to remain an integer, and it's actually going to be the classical index of the harmony. Okay, it's going to be the index of the Fourier coefficient. To give you an example, if what I want to compute is the classical field emitted by an electron moving in an ellipse, I'm going to have a whole tower of harmonies that this electron emits. So the 10th harmony is going to be the classical limit of a delta 10 transition from both sides. And amusingly, actually, I was telling a friend about this today, and I realized that this is the only case that I know of in which all forbidden transitions actually matter, okay? So a delta 10 transition, if you're doing something in the lab, you never have to compute it because it's never good for anything. But here, because h bar goes to 0, okay, all forbidden transitions actually contribute harmonies in the classical limit. Okay, so this is why we actually, in the hydrogen atom, we had to compute all transitions between all levels to get this. Okay. So the classical Fourier coefficient is the h bar goes to 0 limit of the quantum matrix element for the corresponding operator O. According to the correspondence principle, quantum numbers go to infinity, while their product with h is just the classical quantities. But the deltas remain finite and they become the indices of the classical Fourier series. Okay, so please ask me questions about this, because this is like the main formula you're going to see used over and over throughout the talk, if anything's unclear.
So the L's in the cat are the number for the two frequency, the radial one and angular one.
So L is going to be equal to angular momentum over h bar. Before I take
the cat, I'm confused which L is what mean.
Oh, so okay. So I'm starting without loss of generality. Because of spherical symmetry, I'm moving in the xy plane. So L is equal to LZ. Okay, so I could have written M there on the right-hand side, but M is always equal to L because I'm in a planar motion. So actually, it's a little bit of a typo. I could have just written M here in the ket. And
Okay.
so it's not really a typo, but it makes it harder to understand maybe. Okay. Okay. So this sounds like a kind of a heavy formula, but the only thing I need in order to prove it is WQB. Just apply WQB. And let me show you how it's done. So let's take an operator which is scalar. So it doesn't depend on angles. So I'm going to set the same angular quantum numbers on both sides just to simplify the proof for this talk. And now the definition of the quantum matrix element is just an overlap integral between the radial functions of the bra and the ket with the operator inserted in the middle. And the idea is that in the h bar goes to 0 limit, I can just substitute the WKB form for these wave functions. And when I do this, what I get basically is because of the product of these r's, I'm going to get a sine times a sine, which is a cosine of the difference and a cosine of the sum. And the cosine of the sum just goes to 1 because h bar goes to 0. So I'm going to drop it. So the only thing I have left, sorry?
Yes, on your first equation on the left-hand side, you have a sum over delta m, but there's no delta m in the. Is that?
Oh yeah, that's. I mean, the general formula is the sum over delta m, but here, because I chose a scalar operator, then there's a selection rule that only delta m equals 0 contributes here. So I could just drop it. This is just for the sake of this proof. The more general proof would have a sum over delta m. But I just chose to simplify it for the sake of this talk. Okay, so now I got the difference of two s's. And my next move, okay, is I'm going to change variables from r to alpha r, which is the fundamental angle associated with the radial motion. And the idea is that dr to d alpha r is exactly the Jacobian that I have here from the wave function. So when I do this change of variables, it's starting to look very much like the inverse Fourier transform that I want. So it's an operator as a function of alpha r, integrating over alpha r. And now there's this annoying cosine of the delta action, which somehow I want to become my inverse Fourier transform. Okay, so there's a little bit of, there's like one step left to associate this difference between the two actions with a classical quantity. So let's drive this point home. What happens is that the difference between these actions is the partial of the action with respect to E, and then the difference of the E's divided by H bar delta JR. But note that this is exactly what we showed earlier using our quantum to classical relations. So ds to the E is just time. This whole thing is just equal to the fundamental frequency. This is what I showed you a few slides earlier. So this whole difference of actions over H bar goes to just the index of the harmony times alpha. So indeed, this just becomes the defining formula for the inverse Fourier transform, which gives you the Fourier coefficient. It's just a very simple WKB proof of the master equation. And I was kind of shocked that I have not seen it before.
Sorry, Ofri?
Yes.
So I'm really not familiar with the action angle stuff. So somehow it seems like, you know, if I have some bound motion, I mean, in all generality, there's just no way it could be characterized by two frequencies, right? So can you just say a little more maybe about exactly, so are you saying, but you're saying still this is true for any spherically symmetric potential,
Yep.
no matter how, so could you just maybe just say a little bit more about what these things are and why I shouldn't be surprised that everything is somehow can be written as a Fourier transform, whereas I might think if I had a very wiggly potential, things could get stuck at some radius and then transform to another radius, and I could get something that seems it could be very complicated. But you say it's just,
I mean, it's just a matter of yeah.
I mean,
So it's a very
obvious to you,
simple.
but I don't know that this is not familiar to me at all. So that seems kind of
Sure. So the picture that's relevant here is this picture. So I mean, maybe you want to invert it for it to look more familiar. Okay. It's just a potential well. And because this is conservative motion, in a potential well, you're just going to go between, you're going to do libration between the two turning point radii. That's what usually happens in
So I mean,
radial
for
motion.
example, if I imagine, and maybe this is, I don't know, would this be kind of thing be included? So I could imagine that I have some sort of little double wellish thing, okay? And for a while, I'm going over the hump in the middle, but then as I lose energy, I get stuck in one of the two.
Oh yeah, of
ends.
course. But everything I'm telling you right now is for the conservative motion. I'm not having the back reaction.
So if I was just on the edge of being able to go over the top, for example, something here would break down. If I was right on that bleeding edge.
I mean, this is where just the idealized system would not represent nature anymore.
Perverted systems. I'm just trying to understand, like,
So in the idealized motion, right? If you ride on like the Mexican hat, the top of the Mexican hat, right? You're gonna stop there because your velocity is gonna go to 0 there. So you're gonna get stuck up on the Mexican hat. Classically. There's no temperature, there's no friction. It's just classical physics, you know.
okay.
Yeah. So what happens is like, right, the angle just the azimuthal angle just goes like this, right? And the radial motion does libration. And generically, if you pick up like Goldstein classical mechanics or something, you see that you can have a canonical transformation to these action angular variables, which make things simple because let me go back to their definition. You always have a canonical transformation to these coordinates, to these general coordinates, alpha r and alpha phi. And the idea is that if you solve their equation of motion, they actually change linearly in time. So in the context of Keplerian motion, this has a name. It's called the mean anomaly.
Okay.
I don't know, maybe it helps. Okay. Good. So let's do some applications. So first, let me tell you the general algorithm. So we have the master equation. And to prove it, we use WKB. But to actually apply it, we can't use WKB. There's no, again, free lunches, right? If you do WKB just to use the master equation, you're going back to the classical integral you're trying to compute. All right. So to successfully apply the quantum spectral method and compute things you were not able to compute classically, you would have to actually compute the quantum matrix element in its full glory, and only later take the h bar goes to zero limit. This might seem complicated, okay, but it actually allows you to calculate things you just couldn't classically. So whatever your system is, you find the eigenstates, you compute a matrix element, you set the quantum numbers to be their classical counterparts over h bar, and then you simply take h bar to zero limit. This is hard, but it's doable, and it allows you to compute things you just couldn't otherwise. Why can we do things that we couldn't otherwise? So the idea is that the matrix element is an overlap integral over special functions. For example, in the hydrogen atom, these are Laguerre polynomials or confluent hypergeometric functions. Now, when you do the overlap integral of two of these functions, you can use the magic of special functions. You can use the special formulas for how to integrate two hypergeometric functions together, okay? And that has a well-defined answer if you just find the right special function book. And then you take the h bar to zero limit before linking, after linking the quantum numbers to their classical counterparts. And that gets you to compute this inverse Fourier transform, which if you try to do it classically, you just wouldn't be able to do it. Okay, this is like solving all multiples of an antenna in E&M. It's just something that people don't know how to do analytically. Okay, so let's look at applications. As a proof of principle, let me reproduce for you the formula for the radius as a function of time for just Keplerian motion. Then I'm going to compute for you the radiated field at all multipoles, not just dipole, just all the field that's generated from a Keplerian electron.
Great.
Sorry, was there a question?
There's an interruption, but it's
All right.
done.
Oh, okay. And then, of course, with a computed emitted field, we can always form a Lorentz force and see how it back reacts on the trajectory and leads to an inspiral. So once what we compute analytically is the force. And once we compute the force, we can use the force to solve a very simple one-dimensional ODE to calculate the inspiraling trajectory. Okay, so a little bit about Keplerian motion. So now we specialize to just a Coulomb potential, and that leads to an elliptic orbit. And we can link these orbital parameters, this is called the semi-lattice rectum and the eccentricity, to the angular momentum and energy of the problem. And note that the energy is negative because it's a bound orbit. And the two fundamental frequencies are equal, okay? This is a result of symmetry. You might have heard about the Runge-Lenz vector or the SO4 enhanced symmetry of the Coulomb potential, the Coulomb problem. So that's what it is. And that means that instead of a double Fourier series, I just have a single Fourier series over one angle variable, okay? The azimuthal period and the radial period are the same. And quantum mechanically, it means that I can use just the principal quantum number for the harmony. Let's do QSM. So the quantum analog of the quantum solution of this Hamiltonian is just the hydrogen atom. So I'm writing the solutions to the hydrogen atom. These are the eigenfunctions. And I'm using the master equation to find the Fourier coefficient of the radius as the classical limit of this matrix element with the R operator between the bra and the ket. And here comes this magic of special functions. I know how to integrate two confluent hypergeometrics together. It gives me a lengthy but finite formula. These are just normal hypergeometric functions. And now all I need to do is set quantum numbers to the classical quantities over h bar and then take h bar to 0. Yes.
Okay, yeah, Griffin, it sounds like, did I understand from the last slide that you're saying that even when you take into account, radiation reaction, somehow there's only one frequency, in some sense, what does that mean? Is that saying that somehow the orbits, doesn't say they close, what does it say? I mean, is that something that I should be surprised by?
No, that fits into kind of the setup of the, if you remember in the setup of the whole problem, I said that if you want to calculate an inspiral at first order in the mass ratio, to describe it within this order and perturbation theory, you can compute the self-force or the emitted field, pretending that the source is a Keplerian orbit.
This is only to first order somehow, or?
This is first order in the mass ratio, but if you want to take the next order, instead of just computing the self-force, you'd compute its partials with respect to the orbital parameters, and you'd multiply by their dots from the previous order, from the first order.
That still gives you a single frequency, right? It still becomes a secondary order.
Yeah, because every time, because at each point in time, there's a tangential Keplerian orbit, and for a Keplerian orbit, there's one fundamental frequency.
They can never somehow, okay. All right.
The real inspiral doesn't have any fundamental frequency because it's inspiraling, right?
Yeah,
So what you're saying is you have tangential Keplerian orbits at each point in time.
Okay.
Yeah. Okay, so we do a hydrogen atom computation, we get a result, and then we take its classical limit, and lo and behold, we reproduce something that if you open the textbooks for celestial mechanics, that's exactly what you get. So this is the formula for the radius as a function of time. So alpha is just linear in time with the fundamental frequency for Keplerian motion, and we just reproduced it with the quantum spectral method. Moving on. Let's look at the emitted field. This is a little bit of a bigger fish to fry. So let's compute the radiated field from a Keplerian electron. So all orders in the multipole expansion. So what we need to do is we need to take a source and integrate it with the Green's function. The source is just a delta function moving wherever the inspiraling electron is, and the strength of the interaction is just the charge times the momentum over mass. This is like a velocity-dependent interaction. And what you need to do is you need to take the current and integrate it with the known classical Green's function that you picked up from your Jackson E&M. And this Green's function is just, if you open Jackson E&M, this has nothing to do with the QSM. This is just a fact about classical electrodynamics. And of course, what I want to do is I want to do the multipole expansion, which I think is probably an exercise in Jackson, whose solution is this. And now I substitute the current and the multipole expanded Green's function into the formula for the retarded field. And I integrate over some delta functions. So far, nothing to do with the QSM. This is just the Jackson exercise. And this is the result. So what does the result say? There's, as usual, just like any other variable, it's just going to be a Fourier series in the fundamental angle. This is the shape of the multipole. Again, it's a feature of E&M, not a feature of, the QSM. But this M is where the details of the source are. And this is what I'm going to compute with the QSM. So this M is given by the classical limit of a quantum matrix element, which now has P mu. Okay, this came from the current. And then it has JL and YLM, which came from the coupling of the gauge field. It's the part of the Green's function that's evaluated at the source. This is where this J and YLM come from. So I'm going to save you a whole bunch of arithmetics. Okay, this is not an easy calculation, but eventually we did it. but I'm going to give you a little bit of a taste of what these classical limits are. For example, if I want to evaluate the matrix element of a Bessel J, I'm just going to Taylor expand within the matrix element. But the real deal, what the hardest thing to do was to compute this matrix element of r to the power of j in the hydrogen atom. And this is some sum over Laguerre polynomials. Okay, so this seems awfully complicated, but note what it's equivalent to. It's equivalent to an all-order resummation, okay, of perturbative diagrams. So in a sense, you can look at these special functions as guiding us. If you were to compute another loop and another loop and another loop, okay, you'd eventually reconstruct these Laguerre polynomials. Okay, so this is where the resummation is headed. Okay, and we can, of course, in our upcoming work, what we're doing is we're expanding it in the coupling and comparing to amplitude loop calculations. Okay, so a little bit about the results before I wrap up. So this is the emitted field for an observer on the x-axis far away from the electron's orbit. And I'm showing you different orbital parameters. So the yellow and the green are slow, okay? It means they're far away. This thing speeds up if it gets close, right? So trajectories are closer, they're moving faster. And the blue and the purple are fast. And then there's circular and eccentric. And what these things matter is they matter for selection rules. Okay, so things that are slow, only the dipole radiation will dominate. So delta L is always 1, both for the yellow and the green. Things that are fast, there's going to be any transition in delta L that's allowed. Okay, things that are circular are going to have delta N equals delta L, and things that are eccentric are not going to have any link between delta N and delta L. And you can see that the yellow is just, is just a sine wave. And for the fast orbits, the blue and the purple, you have a Doppler shift, which leads to an asymmetry in the solution. Well, if you look at the two eccentric orbits, the green and the purple, they have many multiples, so they don't look that much like a sine wave anymore. And of course, we compared this to numerics, and it's just a perfect match. So you can see the error from numerics, which is just a function of how many terms we took here in this relative error plot. And what I'm showing here is just the different contributions from different multiples. So on the right panel, you see slow motion. Okay, in slow motion, the dipole is going to dominate always over anything. Okay, so the blue is the dipole, and it's way dominating over anything else. And on the x-axis, we have the harmony. Okay, so if you're in a circular orbit, you're just going to have one single harmony. If you're in an eccentric orbit, you're going to have many different harmonies. The interesting thing here to note is for fast motion, there's a certain harmony for which the higher multiples in L dominate over the lower multiples. So it's actually not going to be dominated by dipole radiation. Okay. So I think this is an interesting thing to note here. Any questions about these plots?
So the error is caused by just the numerical error of machine, otherwise.
Oh yeah, we saw 10 to the minus 9, and we were like, yeah, okay, that's good enough for us. But if we wanted to run it for another 15 minutes, it would be 10 to the minus 12 or minus 15. Yeah, this is like an instant plot. It doesn't take like a lot of time to compute. I think it's like a 5-minute run in mathematical. Okay, good. All right, so we computed the field. Why not just derive from it the Lorentz force and the back reaction and the resulting inspiral? And here we're in for a surprise. So remember that I told you that we can parameterize the inspiraling orbit as just a Keplerian orbit with slowly changing quote unquote constants of motion. And their change is given by the radiation reaction force, which you can compute directly from the emitted field, which we just computed. So let's do that. I'm going to skip a lot of details, but we're in for a surprise. Because let's see what dE to dt and dL to dt, this is the change in energy and angular momentum from the classical radiation. And it's starting to look pretty nice. So this gamma SE is just the quantum formula for spontaneous emission, the way you learn it in undergrad, okay? So this is pretty satisfying. The energy and angular momentum lost to classical radiation is the classical limit of spontaneous emission in the hydrogen atom, okay? This is something that I don't think anybody would object to, but as far as I know, it's the first time somebody shows it just analytically. And for the details, I welcome you to read the paper. Okay, so just for kicks, what we did is we solved the differential equation and computed the inspiral, and then we compared our full result to what you would get if you were to just throw out anything but the dipole. There has to be an error which is growing as it's going in. And note that these two inspirals, I ended them at the same time. So you can see that as you go in, there's a deviation between the full computation, which is the green, and the blue, which is the dipole only. And you see they end up not even at the same point. Okay, so this is where the dipole is just not a good approximation anymore for this motion. What we can also do is in the far field approximation, we can compute the waveform the same way you would, the waveform that you get in gravitational waves from a black hole inspiral, for example. And then we can plot this waveform. So in the early moments, the dipole approximation and the full calculation are on top of each other. But at later moments, you see that they have a phase shift between the two of them. Okay. But what happens is the emission is different, so also the amount of energy lost within the dipole approximation or the full calculation is different. So at some point, even the amplitude changes, and this is where at one single time, there are different proximities to the center of the force. So this really teaches us that this result is important. And a similar thing happens for black hole inspirals. As you go in, you just get faster and you cannot just work in the dipole approximation anymore. All right, so let me summarize. The QSM is a method to obtain the Fourier coefficients of classical observables. The delta JR delta L Fourier coefficient of the classical observable O is the classical limit of the delta JR delta L transition mediated by the quantum operator O. And we applied it to compute time-dependent Keplerian motion, the all-multipole electromagnetic radiation from a Keplerian orbit, and the electromagnetic self-force in adiabatic electromagnetic inspiral. And before I finish, let me just give our preview of our upcoming work. What we did is we generalized what you've seen today, both to a fully special relativistic motion and also to unbound motion. So to do that in relativistic, we had to convert the Schrodinger equation to Klein-Gordon. Now you may say that there isn't a proper quantization in this case, but I don't care. The only thing that I need is WKB that works. So I can find a WKB connection between Klein-Gordon and relativistic point particle motion. And for unbound, the Fourier series just becomes a Laplace transform. So we did this both, and we have an expression that's valid both relativistically and for unbound orbits. And the beautiful thing here is that this expression is universal. Sometimes people talk about analytical continuation between bound and unbound orbit. This is an expression which manifestly analytically continues to both regimes. So here's a plot of me using the same expression for bound and unbound motion and reproducing the numerical results exactly. Okay, so I'm going to skip gravity. You can ask about the future gravity directions. There's the interconnections with amplitudes, which you're also free to ask about. I'm going to leave you with where our method is and with respect to other quantum to classical methods. Thank you.
Questions?
Yes.
So I have kind of a, this is a bit of a hobby horse question. So, you know, as I'm sure you know that, if I try to just take the radiation back reaction force, and I just say, I will just integrate it classically with some reasonable initial conditions, I always get runaway solutions, right? And somehow, of course, quantum mechanics knows better. So quantum mechanics knows that that's not what happens. And if you, the fact, I think, you know, technically the reason you're not encountering this here is because you're averaging, you're doing this orbit averaging. And so that somehow gets rid of this, okay? So physically, it seems like this result seems right. Everything is fine. My question is just, do you have any thoughts about this? I mean, that's sort of the paradox, to the extent that there is one, seems to be purely in the classical regime, classical side. It somehow doesn't show up even in the quantum side. But in thinking about this, do you have any remarks about this that you would?
Yeah, so I have been thinking about this, especially since you asked me this question maybe 4 months
I
ago.
keep asking everybody this question. So I thought,
So-
I don't remember specifically asking you. That's exactly what I
Yeah.
would do.
Yeah, so I think, so one, it's not quantum mechanics that solves this, okay? Because already the people that do cell force, I didn't invent cell force, right? So the people that do post-adiabatic perturbation theory and cell force, they do purely classical computations and they don't have runaway solutions. Okay, and the reason I think that's the case is because you're working in a regime where the back reaction is inherently subdominant to the central force itself. It's a small effect. There's a ratio of scales between the time scale for one Keplerian period and the time scale for the loss to radiation. So you're essentially, you're solving your equation, you're within a basin of attraction of the solution of like perturbation theory around a Keplerian orbit. It doesn't mean that the full inspiraling trajectory looks like a Keplerian orbit, but it looks like it's tangential to a Keplerian orbit at each point. And of course, if we talk about gravity, then switch the word Keplerian orbit to just a bound geodesic. So I think what you're essentially doing is you're putting the constraint, which is not just an initial condition, you're telling it at each point, behave like a conservative orbit plus perturbation, plus small perturbation from the radiation. And this is how you're somehow excluding the self-accelerating solution, as I think. And at a more technical level, when we compute our self force from the QSM, it looks more like the Landau-Lifshitz version of the radiation reaction force. So that also is after you kind of don't have the self-accelerating part. Nowhere do I get a force which is proportional to A dot. I don't know if that answered your question.
Yeah, and somehow my question is more like, in principle, there should be a way where I should be able to classically just give you the initial conditions and just evolve, right? But that method always seems to lead to these runaway solutions. So it's not clear, it's still not totally clear to me why this is the right answer, but anyway, I just wanted to hear what you had to say, and I've heard it.
Sure.
When you do the quantum calculation, there's a bra and a ket, not specifying just initial.
Yeah, I mean, you know, there's I think that's at some technical level, it's something like that. I mean, you know, way back, Dirac proposed that you should just put in some final state boundary conditions that eliminate the accelerating solutions. And in some ways, that's what I think all these perturbative approaches do, including Landau-Lipschitz. It's just not totally satisfying, but that's okay. That's just me.
Maybe runaway solutions are proof that you live in a quantum world.
Yeah, no, I'd just like to see why, naively, there's nothing quantum mechanical that's important here, right? I mean, he's using quantum mechanics to do the calculation, but he's doing the classical calculation. So there, in the end, there's no H bar, right? H bar is 0 in the final result.
Yep.
And yet, somehow, quantum mechanics is cutting this off. I don't know. This is the thing I've been thinking about on and off. If there's a rational way of understanding this.
Well, probably, I mean, if you ask what is the solution to the problem which has both radiation reaction and a central force, the answer is probably that there, and in the, in the regime where the radiation reaction is significantly a small perturbation, then there probably is no runaway solution to this problem. There's probably just one solution, which is the inspiraling orbit.
But eventually, when it gets close enough, doesn't the radiation become comparable?
Right. This is where we lose our perturbation theory. And there I can't say anything anymore. Well, let me correct myself. It's perturbation theory not in the coupling and not in velocity. It's perturbation theory in the mass ratio. And the mass ratio doesn't change even when I go in. So it's true that higher multiples will, play a role, and it would have to sum over more multiples, but I don't think you'll lose the perturbation theory in the mass ratio.
So there's no runaway then.
Oh, but maybe what happens is, things that are formally small because of the mass ratio are not going to be so small because of the high velocity towards the center. So I think you're probably going to have to resum your perturbation theory if you're very close to the center. But I don't know, that's just a guess.
You say you work into the mass ratio square. This is perturbation that is. What if you want to go to higher order? How do you do? Or is there a way to do it?
Higher order in the mass ratio, you mean?
In mass ratio, you say.
Oh, yeah. Yeah, okay, good question. So in E&M, there's just no impediment to computing in the higher order in the mass ratio. Okay, because the only thing you'd have to do is now your source is the back-reacted source, which means that instead of just computing the cell force, I'll have to compute its partials with respect to the orbital parameters, but that's something that I can do in days. Okay, so an E&M solved problem essentially, but what people care about is not E&M, right? So if you go to one higher order in the mass ratio in GR though, you get another correction, which is order squared in the mass ratio, which doesn't come from this post-adiabatic perturbation theory. It comes from the nonlinearity of GR. It comes from the fact that there's a Feynman diagram in which you emit two gravitons, but then there's a graviton triple coupling. Okay, so this is a hard thing to compute. And that's actually the bottleneck that's part of the reasons I'm even doing this, is because there's like really impressive cell force calculations to second order, but this triple graviton coupling is a huge mess. What you have to do is you actually have to resum like 1,000 squared terms to compute this triple graviton coupling reliably. And each term in the series in the conventional methods is only known numerically, because it's a numerical integral of a Green's function and a current. So they can't even resum. How do you resum something that's just numbers? Okay, so part of the reason that I'm doing what I'm doing, and I think that there might be eventually like a real impact in terms of like orders of magnitude in computation, is that when you know each term in the sum analytically rather than numerically, you can start thinking about resummation methods instead of just having to sum 1,000 squared terms. So this is where I'm getting at, but of course, we'll have to take it step by step. First calculate, in Schwarzschild, which we already started doing first order, and only then second order.
So if you did this for QCD, there would be 3 gluon vertices. So the same problem, or it's slightly
Yeah.
different?
Yeah, it's probably a very similar problem. This is how what happens when you encounter a nonlinearity. But you can do, yeah. In the right regime of some large mass ratio, you can probably do self-force for QCD if it matters for anything. And if you're in a quasi-classical regime.
Any other,
Do double compute.
any other questions?
I have a question. Can you somehow construct new constant motion with retarded interaction based on your non-perturbative results? Like you show that with retarded interaction, of course, the constant motion in the original perturbative problem is no longer a constant motion.
Right. Mm-hmm.
But can you somehow construct some quantities that's not the same as conserved version of constant motion that help you to solve the problem? Like since you already have the non-perturbative solutions.
Right. That's an interesting question. It should be some kind of volume in the phase space which remains invariant even though you're radiating. Like
Well,
you don't
could
really have a symmetry.
You'd calculate the total energy of the radiation plus the energy of the particle.
Right.
But presumably that's just trivial. After long calculation, you get a trivial result.
Right. So constants of motion, I don't know. What you have is that your old constants of motion are slowly changing because of the mass ratio. And that's what's called an adiabatic invariant, essentially, in classical physics or nonlinear dynamics.
Yeah, and it could be helpful if you could find enough of them and make the original problem integrable.
Yeah, I just don't know why they would be there because they would definitely not correspond to symmetries of the problem. So I don't know why they would be invariant.
I mean, it is striking though that somehow it's striking that the back reaction equations are even local, right? So like, as you probably know, if you go down one dimension or up one dimension, they're not. They're not just given by some differential equation because the retarded Green's function is not localized on the light cone, right? In odd space-time dimensions.
Well, I mean, I cheated a little bit because I didn't compute the self-force with the retarded field. I computed it with the regular field, which is for E&M, it's just the Dirac prescription, so advanced minus retarded over 2. So
Yeah.
So in GR, I would do it with the Detweiler-Whitning prescription, for example.
Yeah, but if you were in odd space-time dimension, you would have to integrate over not just the past light cone. So it's true. You see what I mean? You have to integrate over the inside of the light cone as well. So you're making the approximation that it's instantaneous because the heavy guy is not moving, right? But there's another thing, which is that you don't have to worry about the inside of the light cone.
Right. Mm-hmm.
Anyway, I don't know if it's relevant.
Yeah, I think, yeah, I mean, that has known prescriptions, I think, which I've not dealt with yet, but I know that it's like
Yeah, I was
a
just
solved
thinking,
problem.
you might guess there could be some sort of conserved thing. It's just some higher order, it's just some higher order term in the differential equation, but it's local in time. So somehow asking for something, some weird conserved quantity doesn't seem totally nuts. But if you have to integrate over the entire path, it seems hopeless.
Yeah, I would say the best thing I can hope for are things that are, invariants within the order of the post-adiabatic expansion that you're working. So their change is higher order in the mass ratio than what you need. And then I can use them as constants within my approximation.
Okay, let's thank Ofri again.
Thanks again for inviting me.